Section 2.2 is the second method for solving first-order ordinary differential equations. This is now homogeneous differential equations. We must start by saying homogeneity here is totally different than the definition we have done in chapter 1. This is actually a special definition. Anyway, just like before, we are going to see what is homogeneous differential equation and how do we solve it. A homogeneous differential equation is of this form. If you have the equation dy dx, the right hand side of the equation is a function of y over x. For example, this differential equation, which is y over x plus sine y over x plus, for example, ey over x, you can put everything which shows you that this is a differential equation which is homogeneous because the right hand side is a function of y over x. Everything, all the variables are in the form of y over x. And this is a very straightforward homogeneous differential because we can see that clearly that the right hand side is a function of y over x. This is another example of homogeneous differential equation, but it is not as straightforward as the previous one. This is also homogeneous. You can write the right hand side as a function of y over x if you divide numerator and denominator by x, which is okay. We are not changing anything, we are only changing the form. So this will be 1, this will be y over x, this will be 1 and y over x. So the right hand side is a function, we call it g, not necessarily of course g, a function of y over x. Another example as for this is also homogeneous. It is not like also straightforward like the previous one. This is homogeneous. If we divide numerator and denominator by x squared, we can write the right hand side as a function of y over x. So it will be something like this. This is y over x. So the right hand side is a function of y over x. So it is also homogeneous. A quick way of checking homogeneity from the beginning, if you look here, we could decide from here that it is homogeneous and it will be a function of y over x from the degrees of the terms. Because if the terms have the same degree, for example, this is 2, this is 2, and if you have mix, you add the degrees, 1 plus 1 is 2. If the terms are of the same degree, then definitely it will be homogeneous. Same thing here. This is 1, this is 1, this is 1, and this is 1. All the terms of degree 1, of power 1. So if the terms are all of the same degree, then definitely we're going to have a function of y over x in the right hand side. For example, if you try this one, this will not be homogeneous, even if you divide by x or by x squared, because the terms are not of the same degree. This term is of degree 1, while this one is 2 and this one is 2. So even if you divide by x squared or by x, you are not going to have a function of y over x. For example, if you divide by x squared, this will be 1 over x. This will be y over x squared, that's okay, but this has a problem. So because the terms are of different degrees, then then for sure we know from beginning that it is not homogeneous differential equation. Now here are more examples of homogeneous differential equation. This, for example, number 1 is homogeneous because all terms of degree 1. If you rearrange, you can confirm homogeneity. You must rearrange correctly because rearrangement is going to be the first step. If you divide by x, this is going to be a function of y over x. You see it was x minus y here, but I wrote it y minus x because this is on this side. If it comes that side, you must rearrange correctly because rearrangement will be the first step in the solution. Number 2 is also homogeneous because all terms of degree 2. This is of degree 2 because you are going to add the degrees of x and y and so on. So if you rearrange, you are going to see that the right hand side is a function of y over x. So this is minus xy instead of this. divide by, you can change the sign of numerator or denominator if you are transferring to the other side. If you divide by x squared, you are going to have 2 y divide x square minus y divide x divide 1 minus y divide x square, which is a function of y over x in the right hand side. So it's homogeneous. Number 3 is also a very clear case of homogeneity because of the secant also. If you divide like this, you are going to have secant y divide theta, just like y over x plus y over theta. You see here, because of the secant, or the secant is a very strong indication for homogeneity here, or at least for saying that the differential equation is most probably going to be homogeneous. Because if we did not have theta here, if we did not have y divide theta, then this is for sure a differential equation which is not homogeneous. Because when you are dividing by theta, you cannot divide the angle. So if you have a sine or a cosine, if it is homogeneous, then it has to be from the beginning y over x or y over theta. If it was not, then for sure this is not homogeneous. Number 4 is another example. You can divide y by x times, because you have ln y minus ln x, the minus can be written as divide like this, and you have a function of y over x on the right hand side. So this is also a homogeneous differential equation. This is not homogeneous because of degree 2 here. This is degree 1 and 1, so the degrees are different. This is not homogeneous because of 1, because the 1 is of degree 0. You see, you can have 1 at the end like this after dividing, but not before dividing, because if you divide by x squared, for example, here 1 will be 1 over x squared, which is not a function of y over x. So this is of degree 0, while these are of degree 2, so we have different degrees here. So this is not a homogeneous differential equation. So now we have seen what is homogeneous. We have seen that we can check homogeneity by looking at the degrees of the terms, and then after rearranging, we should have a dy dx equal a function of y over x. Now, how do we solve homogeneous differential equation? This is homogeneous. Now the right hand side is a function of y over x. We have to say y over x equal v, which means that the right hand side will be function of v, which is here. We're going to replace it on the right hand side. We have also to change the left side, so we have to find dy dx. If v is equal y over x, then y is equal to xv, and dy dx is a product rule here, so we have x times dv dx plus v times derivative of x, which is 1. See, derivative of v is not 1 because v is of y, so derivative of v is dv dx. Anyway, this is dy dx, so we have to replace it in the differential equation, which is a homogeneous, so the right hand side is a function of y over x. So we are going to have v plus x dv dx, this is dy dx, and g of y over x, it will become g of v. See, this side is always the same. Now, which is what, now looking at this equation, it is clearly a separable differential equation, which means that any homogeneous can be transformed and can be changed into separable if you put y over x equal v. If you separate and solve, this is going to be your solution. This is always 1 over x, this is always v. This will change in every question because you are going to take it from the right hand side. So that was the solution procedure. Conclusion: every homogeneous differential equation can be converted or transformed into separable differential equation by putting or by substituting v equal yx or v equal to xy. This is actually, we use it if we have dx over dy in the question. Most of the questions in the book are dy dx, so we take v equal y over x. Now we are going to solve a couple of exercises. So looking at this equation now, it is not separable because you have a function of x plus function of y. But it is homogeneous because we have all the terms of the same degree. This is of degree 3, this is of degree 3, and this is of degree 3 because it is 1 plus 2, which is a 3. So we know it's homogeneous. We should rearrange. Okay, this is x cubed plus y cubed divide xy squared. Okay, you must double check before you move from this step, because if you rearrange incorrectly, you are going to solve a different equation. Anyway, if you check by cross product, okay, you are going to have dy xy squared, but there is a minus here. The reason it is minus here because it is on this side, it will be transferred to the other side. Anyway, this is the rearrangement. Okay, we are going to divide now by x cubed both sides. This is by x cubed and this is by x cubed. So this is 1. You see, if the terms are of degree 3, then we divide by x cubed. If the terms are of degree 2, we divide by x squared, and so on. So this is dy dx. Then we are going to let y over x equal v. So y equal xv. This does not change in every question, these three things. This is equal to v plus x dv dx. Replace this in the differential equation, which is here. So we are going to have v plus x dv dx equal 1 plus v cubed 1 plus v cubed over v squared, which must be separable. This must be separable because we have used this procedure on the general case, and so separate. Bring the v on the other side first. So xv dv dx equal 1 plus v cubed over v squared minus v. This is equal to 1 over v squared. You can either combine a fraction, or you can divide this by v squared and divide this by v squared, so it will become v minus v. So this is 1 over v squared. This is x dv dx. Now separate the variables. So you have v squared dv is equal dx. This is always, by the way, 1 over x. Integrate. So this is v cubed over 3 equal to ln x plus c. Then the last step, replace v by y over x, divide 3 equal to ln x plus c. One more exercise is exercise 4. You see, this is already dy dx equal to, so it's rearrange all the terms of degree 2, so it's homogeneous. We are going to divide by x squared only, numerator and denominator. So we are going to have 1 plus 3y divide x squared divide by 2y over x. Now we are going to let v equal y over x, so y is equal to xv. So dy dx is equal to v plus x dv dx. Now substitute in the differential equation. So you have v plus x dv dx equal 1 plus 3v squared divided by 2v. Transfer v to the other side. So you have 1 plus 3v squared over 2v minus v. Combine fractions so you can separate easily. This is 1. This is 1 plus 3v squared minus 2v squared. This is x dv dx. So this will become v squared. So 1 plus v squared over 2v. This is x dv dx. Now separate the variable. This is always 1 over x. Bring this here, so you have 2v over 1 plus v squared dv. Integrate both sides, so you have ln 1 plus v squared equal to ln x. Instead of c, let's write ln c. You see, c can be written anything, not necessarily c. So here, since we have everything ln, we will write c as ln c because we can put it as a product. And then after that, since ln is equal to ln on both sides, so 1 plus v squared is equal to xc. And then you can put, instead of v squared, y over x. This is your final answer.